Hi, and welcome to this new video. This is not episode 4, which will be uploaded very soon, but a video in which I describe our last accepted paper, GPU Accelerated SIFT-aided Source Identification of Stabilized Video. It's a paper we submit to the ICIP conference that this year, 2022, takes place in Bordeaux, and that was written in collaboration with Cecilia Pasquini, Giulia Boato and Stefano Dell'Anna from the University of Trento and Professor Fernando Perez Gonzalez from the University of Vigo in Spain. In our paper, we tackle the problem of source identification of stabilized videos, which consists in identifying the device, or better, the camera or the smartphone, used to record the video when digital stabilization is applied. But why this is a problem? Well, video stabilization takes place every time we record a video and we want to reduce the amount of shakings introduced by our unexperted hands. And these shakings are reduced by applying spatial transformation through a 3x3 matrix. However, every time we use video stabilization, by applying a series of spatial transformation, we not only change the position of the pixels, but also we desynchronize a scant residual or signal introduced by the sensor of our camera called photoresponse non-uniformity or PRNU that we also use in task of source identification. Different choices than the PRNU could be adopted, for instance, features representing the camera acquisition process or Noiseprint, which is a residuals extract by a deep neural network. Nevertheless, both of them are not as representative and unique as the PRNU, and residual extracted by deep neural networks such as Noiseprint cannot be used very often in courtroom due to their not fully explainability. Also for this reason, the state of the art is mainly represented by method using the PRNU for source identification of stabilized video. And two illustrative examples are the ones that we select to compare our method with, which are fixing device attribution problem for stabilized video sequence and a modified Fourier-Mellin approach for source device identification of stabilized video. Both these two methods try to solve the problem of source identification of stabilized video by estimating 6 of the 9 parameters used to reverse video stabilization spatial transformation, working just with E-frames and opting for more performant optimization algorithms such as particle swarm. Furthermore, the modified Fourier-Mellin approach propose a novel solution for the estimation of the rotation parameters. In contrast, both these methods suffer from the high computational complexity of problems like source identification of stabilized video. Indeed, to fully revert the video stabilization, we need to estimate up to 9 parameters. We need to do this for every single frame of the video, and we need to check for every single frame all the possible combination of ranges of these parameters. Furthermore, we want to do it by being computationally efficient, but of course the CPU and its poor parallelization capabilities doesn't suit very well these kind of problems. For all this reason, we propose an algorithm that works entirely on the GPU, that serves as a computer accelerator, and that exploits SIFT key point to locate the less stabilized frames and to efficiently invert the stabilization that was applied to this one. Thus, our method can be summarized in these 3 intuitions. The first intuition consists in using the GPU instead of the CPU, as programmers did in early 90s in gaming industry. In their case, they used the GPU to render, model and transform more rich and better environment, and in our case we use it to check the huge amount of transformation coming as the product of the infinite numbers of combination of ranges of parameters we need to check. The second intuition consists in observing that if the displacement between 2 frames is low enough, then it will be easier to reverse their video stabilization. For instance, if we were able to reverse perfectly or almost perfectly stabilization to the first frame, then using SIFT key point we can co-register the second one with respect to the first one. So how can we locate the less stabilized frames without losing time checking all of them? And for these points come our third intuition. In fact, by using SIFT key point, we can locate the less stabilized group of pictures and work with just this one to then attribute this video for a certain device or another. But how can we do it? Well, just starting from all the gap, we just measure the displacement between the first E-frames and the last one, and we select the gap or group of pictures which has the lower value of displacement. At this point, all this intuition can be summarized in this flowchart. in which, giving a video and a device, we pre-compute offline a camera fingerprint, or better, a reference ground truth that we use to compare with the PNG of the video to find a match between the video and the source, and that we compose with 100 flat images taken all from the same device and that were adapted to frame size dimension. After that, we estimate the less stabilized group of pictures using SIFT key point, and we invert the stabilization to the first E-frames using a breadth-first search. Thus, a first PCE or peak of correlation energy value, the optimization function used to estimate if a video was or not taken with a certain device, is estimated from the first E-frames. And this one will be used with all the others at the end of the execution of the algorithm to estimate if the video was or not taken with that specific device. Consequently, and for the rest of the frame, we do nothing more than co-register one frames with respect to the ones that comes before, but always checking that better value of peak of correlation energy or PCE value could not be obtained by slightly transform and adjust the transformation estimated during the co-registration phase. At the end of this process, for each frames of the gap we analyze, we obtain a PCE value that are averaged together and compared with a threshold we set through a ROC curve. Our method outperformed the state-of-the-art both in terms of ROC curve, I rendered the curve, true positive rate, and time consumption, demonstrating the suitability of the GPU in problems with a large computational complexity as this one, for instance, and the suitability of SIFT key point for localizing and identify the group of picture of less stabilized frames, and then invert the stabilization and work just with this one to proclaim or not a match between a video and a suspect device. Moreover, we were able to estimate all 9 parameters of the transformation matrix we used to reverse the video stabilization while working with up to 6 times the frames of the state-of-the-art, and we do so independently by their frames type. Indeed, the state-of-the-art only rely on E frames, instead we can work with E, P or B frames independently by their type. Nevertheless, this is just the beginning, because our method can and has to be improved under certain aspects. For instance, we noticed that it underperformed with respect to the state-of-the-art on device 6 and 25, and this mostly for an incorrect estimation of the less stabilized group of picture. To improve our method on this aspect, we thought to study more sophisticated and also deep learning based techniques so as to estimate with this one the less stabilized group of picture and also reverse the video stabilization. Another purpose we have for the future is to extend our method so as it can work more into the wild, for instance in presence of social network compression. And this is all for today, so I really hope you enjoyed this video, even if the light changed quite a lot. I started with the sun, then it became cloudy, now it's raining, so I had to adjust again the illumination. If you have comments, doubts or questions, the comment section is down below. If you enjoyed this video, please leave a thumbs up and we catch up in the next video.